Okay, so I want you to recall the discrete form of the constant density incompressible Navier-Stokes equations. We wrote them in this form for the Ftcs scheme, forward in time. You see it on the left-hand side for the time derivative. And we have the advective and diffusive terms written as A and D and minus pressure gradient. A n means this is a function of un, and dn also a function of un. So n designates using old known information. N plus 1 is information we want to predict. And we also want to satisfy the mass conservation constraint, the incompressibility constraint at n plus 1. Hence, div u n plus 1 equals 0. Now, recall the projection method, where we split the equations by saying we're going to compute we're going to solve the Navier-Stokes equations without the pressure gradient, because we don't know, there's no explicit equation for the pressure. So we take this form, get rid of the pressure gradient, solve for a provisional velocity field called u star, and then we correct u star with this pressure gradient. From this equation, we can derive an equation for the pressure. If we take the divergence of both sides, we can make sure that div u n plus 1 is 0. We want to set div u n plus 1 is 0, so that gives us an equation for the pressure, and we're good to go. So we are all familiar with this now. Okay? Okay. This is, I don't know why I put this slide here, but this is essentially the algorithm. You first find the temporary provisional velocity. Next, you solve for the pressure. And finally, you correct for the velocity. And in algorithm, emerges, you set initial conditions, u0 and initial pressure. You compute the fluxes, advective diffusive fluxes. Then you solve the pressure Poisson equation. You can either put these in u star and then take div u star over delta t, or you can expand the whole thing. It's a matter of convenience. And then finally, you do the time advance. Okay? So that's the FTCS scheme. Okay? Now, what are the time step limitations for the FTCS scheme? I told you in the past that as a starting point, we take the stability constraint, the stability limit for the linear advection diffusion equation. It works pretty well for the most part, and it kind of sets an upper limit, because in the best of cases, we're going to be at that linear stability condition, and the worst case is going to be much lower. So that gives us actually an upper bound for the time step limitation. So doing an analysis based on that time step limitation gives us an idea of what we can do with this scheme, forward in time, central in space. So remember that we had two time step limitations for the linear advection diffusion equation. This is the diffusion coefficient. In this case, it's the kinematic viscosity, mu over rho, or mu, whichever. So that's 4 nu over maximum velocities. Now, you can choose those based on the maximum velocity of your initial condition. And you can update that time step limitation as you move in time, because maybe your flow is gonna develop either larger velocities, like in the channel, parabolic channel, right? You got to 1.5 in the center, right? You started at 1 and the initial condition at the inlet, but then your maximum velocity was 1.5. So you gotta take that into consideration. Okay. Now, to simplify this a little bit further, I want to assume that Umax and Vmax are equal, and they're equal to u. So that gives us, that turns this condition into nu over u squared, and we still have this condition as is. What I'm after is writing this in as a function of a dimensionless parameter. Now, what's the dimensionless parameter for the equations I showed for the incompressible Navier-Stokes equations? The key dimensionless parameter, if you normalize the equations, Reynolds number, right? It's a Reynolds number. So I want to write these time step constraints as a function of the Reynolds number. Okay? So Reynolds number is ul over nu. So I need a time scale, a length scale L. So I'm going to introduce a time scale, tau, in seconds. That's L over u. So meter over meter per second, that's going to be in seconds. Okay? And then I'm going to define a dimensionless time step, delta t prime. That's delta t over tau, which is L over now. Now, what that does, once you do the substitution, it turns these two time step limitations into these two guys. Delta t prime less than 1 over Re. You can imagine 1 over Reynolds number. And then delta t prime less than some coefficient, times the Reynolds number. Okay. Now, this is a problem. Okay? Why? What happens at small Reynolds numbers? This guy is going to go to infinity, so we're not worried about that, but this guy is going to go to 0. Okay? What happens at large Reynolds numbers? This guy is going to go to infinity, but this guy is going to go to 0. So we're stuck between a rock and a hard place for the Reynolds number. So in other words, this FTCS scheme works okay kind of for average for Reynolds numbers between, let's say, 1,000 and 100,000 possibly, or 10,000, okay? If you like that. But depending on your time constraints for getting the problem solved, this may not work for you. So let's plot this. So if you plot delta t prime versus the Reynolds number, the first constraint, 1 over RE, is going to give you this curve. So the first constraint is telling us, as long as delta t prime is below this curve, we're OK. But this guy is going to constrain this further. And what is this guy in this space? It's a straight line. Okay? And that straight line depends on this grid spacing h. Okay? So as you increase h, the slope is going to go up, right? But for a given Reynolds number, for a given Reynolds number, so let's say your Reynolds number is approaching 0, this guy is going to be so low over here, that's going to put your time step over here. Okay? And you can find kind of the maximum delta t you can take for a given Reynolds number, et cetera. But the point is that this is an annoying limitation. Okay? At both ends of the Reynolds number, at both extremes of the Reynolds number, it looks like our time step is really constrained. Okay? So how do we fix this? The simple remedy is to attempt to use implicit methods. So for low Reynolds numbers where viscosity is dominant, so diffusive terms have a significant impact, we go implicit on the diffusion terms. Okay? So you can solve the advection terms explicitly and keep the diffusion terms implicit. You put n+1 on the diffusion terms, and then you have a nonlinear system of equations. You deal with that. You know how to do nonlinear systems. Okay. Now, for large Reynolds numbers, we essentially approach a hyperbolic regime, right? Because the diffusion is becoming less and less dominant, although we have turbulence effects. We'll talk about that later. But foregoing turbulence effects, at high Reynolds numbers, you want to start using limiters. Okay? You stick with advection schemes. You can stay explicit, but you got to use limiters, okay, for high Reynolds numbers. Now, as the Reynolds number increases, you're going to add a turbulence model, which effectively, as we're going to see next week, is going to add viscosity, an artificial viscosity to your equations, which will stabilize some of the oscillations you may get in your advection. Okay. So that leads us to a set of other schemes based on implicit or fully implicit or semi-implicit methods. Okay. So now you may ask, why don't we just go fully implicit? Okay, for all Reynolds numbers, who cares, right? So you do something like this. This is one standard form. Actually, this is a typo here. This should be DUM. So we're combining advection at n+1, advection at n, and dividing by half. It's a standard way of doing it. Or you can just go fully implicit n+1. This is rarely used, if ever. No one uses this system of equations. It leads to a very complicated nonlinear system of equations that is very difficult to solve. No one hardly ever uses that. And because you also have implicitness with the dilatation constraint, so it's like it makes the problem twice as hard. Okay, so you're solving the nonlinear system coming from this, and you're constraining on this guy. It becomes very difficult to solve. There are alternatives, though, that allow you to add implicitness to your system of equations. And one of the most popular ones is a combination of Adams-Bashforth and Crank-Nicolson. So Adams-Bashforth is a time integration method. Crank-Nicolson is also another one. And if you combine the two, you can get the following interesting formulation. So notice the time levels n+1, n, and -1, n, and n+1. So we are implicit on diffusion, okay? But everywhere else we are explicit. But you also have one previous time level. So you got to carry two previous time levels, n minus 1. Okay? And we also want to satisfy div u n plus 1 equals 0. So the way we solve this, we split as usual. We go for the projection. So provisional velocity minus un over delta t. We keep the advective terms and the explicit diffusion term, and we let these guys be part of the projection. Okay? So then, when we project, we do this form. And you notice that in this case, so while we can take the divergence of this to get the solution, the equation for the pressure, the diffusion term is implicit. Okay? So we have an implicit correction equation. So you have to iterate to converge the pressure. So you have the pressure linear system and the diffusion involved. Okay? Gets a little bit more complicated. It's doable. Okay? And then with div u n plus 1, actually, sorry. So when you take, sorry, I forgot that this is actually incompressible. So div of dn plus 1 is actually 0. Because in the constant density case, what is the diffusion term is del squared u. Okay? And then if you take the divergence of that, that's 0. Okay? So it actually just leads you to a simple equation for the pressure. Okay? But when you go and substitute back, you have to be careful at how you treat this implicitly, okay? Because you got to solve for un plus 1 from this guy, okay? Because so when you go back, once you find p, you know u star, you want to find un plus 1, so that's where the implicitness is. So the correction equation is implicit. Another popular method is the one by Kim and Moin. So it takes the same form as the Adams, Bashforth, Crank-Nicholson, okay? But the splitting is different now, okay? The way they do the splitting is they keep the advective terms, they keep dn, but then they use d star. So this equation is implicit now, in this case, okay? This guy is implicit. Remember, we're using this guy to solve for u star. So they made the u star equation implicit, okay? And then we follow as usual. But notice one thing here. The splitting for the correction equation, they do not put a pressure here, they put a phi. Because actually the right-hand side of this equation is not the pressure, it's something else. We'll see what it is. But they call this phi. Now, we always said that the pressure is not actually a physical pressure, it's just a quantity that helps us to enforce mass conservation. Okay, it's just this free parameter that allows us to enforce mass conservation. So this is a great example of doing just that. Okay, so now when you do this, you solve as usual del squared phi. You still have a linear system of equations for phi, or the pseudo pressure, and div u star you compute from this implicitly. Now, how do we still need to relate phi and p, because we want to in the end go back to the original equation. Okay, so what do? We add the first two equations, and we add and subtract a dn plus 1. So you can go through the math yourself, and then you can show that when you do this, this is actually what grad p looks like. So to get grad p, after you solve for phi, you do this thing to get grad p. Okay. So in other words, if you use this splitting, and this actually implies that grad p is 1 over 2 d star minus dn plus 1 minus grad p, and this guy is del squared phi, okay? Because the divergence, so these guys, they come from the divergence of this equation, okay? Anyway, just an illustration. All right. Now we move on to another class, an entirely different class of algorithms. So what we've been dealing with are projection type splitting methods, okay? And you don't have to implement any of those. It's just methods that are out there. If you're doing a project at some point and you feel you want to go implicit, this is one idea to pursue. You got to go dig up the paper, see what they've done. There's a lot more details involved. I haven't implemented any of these methods because I have no need for them, because I operate in a space where I don't need to go fully implicit, okay? The type of problems we solve in our research, we don't need implicitness. Now, who's heard of the simple algorithm? In Fluent or COMSOL? I don't know if they have it in COMSOL or star CCM. Anyone heard of the simple method? You've heard of this. How? Where? Okay. Okay. Okay, so the simple family of algorithms, it's funny, those two guys, Patankar and Spalding. So there's this guy, this classic textbook, Numerical Heat Transfer and Fluid Flow, by Suhasvi Patankar. Am I pronouncing it correctly? Yeah. So brilliant guy. He set the foundation of a big school of thought for finite volume methods by his book. And if you remember Brian Spalding in my first lecture, who promoted the use of CFD and across the world and the use of commercial software. So these two, they came up with a class of algorithms and methods to do finite volume. But you'll find in the literature that there are two schools of thought. The people who follow nomenclature that I've introduced to you, and the people who follow the nomenclature introduced by Spalding and Patankar and his school of thought. And I'll show you that nomenclature in a second. Which one is better? I think if you speak both languages, you win. Okay? So go and speak both languages. All right? So both nomenclatures. And I'll allude to their nomenclature very briefly. So what does SIMPLE stand for? Stands for the semi-implicit method for pressure-linked equations. So these guys are obsessed with acronyms. You will see that they have the simple algorithm, the simpler algorithm, the simplex algorithm, the simplest algorithm, so which is simpler revised, simple corrected, simple ST, I don't know, standard, whatever that means. Anyway, so but they all are based on the simple algorithm, which I'm going to introduce now. It was originally proposed for steady-state problems. So if you want to do the steady-state Navier-Stokes equations, that's where the original formulation arose. You can easily extend it to unsteady flows, and it has been later extended to flows at all speeds, and that's an important issue we'll discuss at the end of this lecture, and improved over the years. But the basic, the original simple algorithm is pretty straightforward. Okay, so we start with the steady-state Navier-Stokes equation. So we dropped the the transient term. We have steady-state equation. Okay, advection, diffusion, advection minus advection plus diffusion minus grad p equals 0, and div u equals 0. Now, when we discretize, and according to the nomenclature followed by Patankar and his school of thought, this is what we get. So think of this, think of advection, diffusion. Remember, they are a stencil, right? So you have ui plus 1, and you have ui, and you have ui minus 1, and you have uj plus 1, and uij, and uj minus 1, uk plus 1, uk minus 1. You may have uk minus 2. Who knows if you're doing second order upwind. The bottom line is that you have a coefficient that multiplies the center value plus a bunch of coefficients that multiply neighboring values. So if you remember the SOR method, or a basic iterative method, the Jacobi iteration for linear systems, that's what we did. We took the diagonal term and solved for that using the off-diagonal term. So this is the same ideology here. The same mentality is that upon discretization, we're going to separate the coefficients that multiply the grid point ijk from all the other terms that connect the neighbors. Clear? And we write it in this form, APUP. So P is the grid point in question. So that's ijk equals some summation of a coefficient that multiplies a neighboring value. So it's a weighted sum of neighboring values. That's what a discretization is. And it's a great way to think about things. Okay? So there's no time-dependent term here, but you can add a time-dependent term, which is going to impact this guy. Okay? And we have a pressure gradient. We leave that as is. And div u equals 0. Div u, we want to enforce div u. And you can discretize div u in the same way. But our goal is to satisfy this equation subject. So find up such that div u is equal to 0. Okay? All right. And the summation over neighbors, of course, it contains the advective and diffusive terms. Okay. So now what happens? In practice, the way we start solving this, how would we solve this equation? How would we go about solving this equation? So let's say I give you an initial pressure. Okay? Give you initial pressure, P star, a gas pressure. You take P star and you plug it in this equation. It's going to give you a velocity field. So that velocity field, does it satisfy div u equals 0? Not necessarily, unless you're very lucky and you gave the right pressure. But it's not necessarily going to satisfy div u equals 0. So let's call the resulting velocity that comes from p star, let's call it u star. Okay? Now the next step is to find a new p star, okay, that makes u star divergence free, that pushes u star towards being divergence free. And that's the gist of the algorithm. If we are starting with a pressure guess for p star, using this guess, we're going to solve this equation above for a velocity field that we're going to call u star. Okay? So if we take p star, we can solve this equation for u star. Okay? That's a linear system of equations that you can solve. Okay? Now, our aim is to correct the pressure and velocity until we satisfy this guy. Remember, there's u, that's the original equation, with div u equals 0. There's this guy that doesn't satisfy div u equals 0, so div u star is not 0. So we want to correct both p star and u star so that they can get us to u and p. So we propose the following decomposition. Let's say that the true u is the guessed u, the incorrect u, plus a correction. And the true p is a guessed p, incorrect p, plus a correction, p prime. Okay? So when we do this, okay, can do this. Now of course, we want, the next step is to get an equation for the corrections. Okay? So how do we correct? We need an equation for the corrections. Okay? We need an equation for the corrections. So what I'm going to do next is take this guy and subtract from it this guy. So u minus u star is u prime, right? So if we take that difference, that's going to give us an equation for the corrections. They all look the same, right? So the correction satisfies the governing equation. The guess satisfies the governing equation. So, yeah. OK. Now, there's a problem here. Because we have one equation. So again, that's the same problem for. So we've moved the problem around. We didn't have an equation. We had 4 equations and 4 unknowns, but no equation for the pressure. So now we have this equation, and it has 2 unknowns in it, p prime and u prime, and it's underspecified, right? So we have one equation but 2 unknowns. So the first step to fix this issue, remember we still haven't used div u equals 0. So we're going to use that next. But before we get there, we're going to make the simple algorithm makes the bold assumption to neglect the neighbor terms, the advection and diffusion terms, advection and diffusion contributions over here, because it complicates the solution of this algorithm. When we go to more advanced simple algorithms, the simple R, the simple C, simplest, they don't make that assumption. But the initial introduction of the simple algorithm, they neglect this term. Okay? Don't hang out on it because it's an iterative procedure. Worst thing is this is going to do is affect your convergence rate. Okay? And then you can over-relax or under-relax based on how your convergence is operating. But let's make that assumption. So that simplifies our correction equation. Okay? Next, so we still have a problem. We want to solve for both u prime and p prime, but we have one equation. So we need to eliminate u prime somehow. Next, we substitute u equal u star plus u prime. Okay? So that tells us that we take u and put it up here. So we get AP UP minus AP U star equal minus grad P prime. Now remember, we haven't used mass conservation. So what do we do next? What? Yeah, we take the divergence of this equation. Okay, so we take the divergence, and now we want div UP equal to 0. We want this guy to be 0, right? That's what we're trying to solve for. Okay? And we know U star, so that leaves us with P prime. That gives us an equation for P prime that's pretty darn similar to the projection method. Really, they're kind of pretty similar, okay? Except that U star is going to be a little bit different, and the assumptions we made by neglecting these neighbors is going to mess up the correction, affect the convergence rate. Okay, so the algorithm is simple. Guess a pressure field P star, solve the momentum equations for U star, solve for the pressure correction P prime, and you neglect the summation over the neighbors, and then correct the pressure, and then correct the velocity. Okay? And rinse and repeat. And that's the simple algorithm. And it's an implicit method. It keeps iterating, and you're solving a Poisson equation at every iteration for the correction. Okay? So if I were to ask you, in other words, can you do a projection method for the steady state Navier-Stokes equations? How would you do that? It's a similar procedure. You can do the decomposition, say, U star minus U, et cetera, solve without the pressure, and then solve for the pressure, and then keep iterating. So you're still solving a pressure equation at every iteration. Okay? It's expensive. You're solving a linear system every iteration, because at the end, your correction is going to be 0. Once you hit 0 for the correction, you got the solution. Okay. Now, other simple type algorithms. As I said, the convergence rate is slow for the simple algorithm because we neglect these neighbor terms, advection, and the diffusion terms. There are other algorithms, such as the simpler or simple R, simple revised, where the pressure correction equation is used to correct the velocities only, but another equation is derived to correct the pressure. So that tries to circumvent the problem of the summations. You can read up more about this from the Patankar book. We have it in the ChemE library. And the simplex algorithm, simple corrected, et cetera, a bunch of other algorithms. Okay? So that what we discussed so far is ideas for doing implicit, going semi-implicit somehow, a bunch of methods using projection methods. We discussed an alternative to projection methods, okay, the simple class of algorithms. Now we're going to try to go higher order in time. And the question is partly about accuracy in time and partly about stability, because we know that the time integrator interacts very tightly with the spatial discretization. Okay? In your homework 6 that you're going to do, in problem 1, you're going to show that the forward in time and the K scheme, or a central scheme for advection, is unconditionally unstable. We've showed this several times before. But then you're going to show that the split scheme, or the predictor corrector, is stable. So the time integrator changed the stability characteristics and the stability boundaries of the method. Okay? So that's what we're going to talk about next. And I'm going to stick with explicit methods, because I'm assuming that we are in a Reynolds number regime where the time step limitation is not that overwhelming, where our time scales and length scales are not that big of a deal. So everything is at the same time and length scale. So the problem, in other words, is not stiff. Okay? So when do you use implicit methods? When you have scales that are very different. So you have something that's happening really fast and something that's happening really slow. The thing that happens really fast is going to constrain you, because if you skip that, it's going to blow up your system. So then you use implicit methods to say, look, I don't want that fast time scale to limit me. Okay, so I want to make the system to advance at a reasonable time scale, a time step. Okay? So if you don't have that problem, if all your scales are really fast or all your scales are really slow, it doesn't matter. Just use an explicit method. If all your scales are of the same order, you can use an explicit method. And besides, it's very simple to kind of discuss and present. Okay, so I'm going to present the Hoin method, or the RK2 strong stability preserving. It's a second order in time method, and it can be constructed very simply by taking a forward step. Pardon me. So we first do a splitting, U star minus UN over delta T. Again, we neglect the pressure. Okay. Now, for this stage, for this step, so this is simply a forward Euler step. The one way to explain Runge-Kutta methods, or going higher order in time, is improving our guess for this slope, getting a better guess for the slope. Remember, when you use the forward Euler method, you're using the slope from UN. As we say, UN plus 1 minus UN over delta T. On the right-hand side, everything is evaluated at UN. So you're using the slope from the past to predict the future. Okay? The gist of RK methods is to improve that slope by using multiple forward Eulers. So you do a forward Euler at n, maybe you do a forward Euler at n plus 2, and then a forward Euler at n plus 1, and then you average the slopes to get a better estimation of the slope. Okay, so that's what the idea behind explicit RK methods is. Okay, so now when you think about it this way, we're doing a series of forward Euler steps. You want to project at each step. You want to satisfy mass conservation at each step. At least that's what we learned. Okay, that's what we know we should do. So in this first step, U star minus un over delta t is minus a n dn, and then that gives us a equation for the pressure. And note that I call this P star because that's an intermediate pressure in the middle of this first step. And then the result of the first step, I'm not going to call it un plus 1, it's u1. This is the first guess. This is not, if we were to stop here, this would be just a forward Euler. Okay? But no, we're going to use this one and do another step and then average both steps. Okay? So it's just a forward Euler step, okay, in the first step. Now that puts us at technically what we called in the past n plus 1. Okay? So we moved from n to n plus 1. Now we're going to take another forward Euler from n plus 1 to n plus 2, or from 1 to 2. I'm not going to call them n plus 1 and n plus 2, not to confuse the nomenclature. So then we take another forward Euler step, and we do the same thing, but with respect to the state at 1. So u double star minus u1 is minus a1 plus d1, everything evaluated at this value. We do another pressure projection, and we correct. So that gives us u2. That gives us a value essentially at n plus 2. So we've taken two steps, two time steps. Okay? First one for forward Euler, then another forward Euler. So now we have two slopes. Okay? And if you average the slopes, the final step tells you, if you go back to n plus 1, the better estimate at n plus 1 is the average of un plus u2. Okay? And just with that, you get second order accuracy. Okay? Just doing that, you get second order accuracy. Okay? Now there are issues with this. And before I discuss the issues, is this divergence free? So what is div un plus 1? We're going to stay here until one of you answers. So what is div un plus 1? Okay, so let's forget the half. So we have div un and div u2. Okay, is this 0? Is div un plus 1 0? Is div u, so you ask yourself, we have div un and div u2. Is div u2 0? Yes, because we made it divergence free. Is div un 0? Not necessarily. If your initial condition is not divergence free, then you're going to carry this divergence along. One fix for this is you take your initial condition and just do a one-step forward Euler, correct that initial condition, and call that your initial condition. Okay? So that's one fix to this. Okay? But keep that in mind, because you may carry this in your algorithm all along. Okay? Okay, so I'm gonna formalize this discussion just a little bit, because the issue here is that, okay, we didn't necessarily satisfy un, the divergence of un plus 1 is 0, and we paid for two projections per time step, because we did two time steps within the time step, essentially. And we paid for the cost of two projections, and we didn't get divergence free, unless we correct for the initial condition. But that's a problem. You know, I don't like this. So let's formalize things a little bit. Let me remind you of what the RK2 or the Hoin method is. For a system, for an ODE, d phi dt equals some right-hand side. Remember, once we discretize in space, we have a bunch of ODEs for the Navier-Stokes, right? System of ODEs. That's the method of lines that we've been using all along. So time integrators work on ODEs, and we have a set of ODEs with the Navier-Stokes. But for the Hoin method, or the second order method we just discussed, we call the first step, the first Euler step, as stage 1. I'm going to call this S1. And that's phi star is phi n plus delta t right-hand side at n. And we did a projection here. So this is just for an ODE, not the Navier-Stokes. And then we had a second stage that I'm going to call S2. So keep those in mind. S1 is the first guess for the slope. S2 is the second slope. And then final stage, Fs, is the averaging of the slopes. Okay? So phi double star for S2. And the final stage is the average of phi n and phi double star. Okay? Now, for the Navier-Stokes equations, we have a few options. Okay? We can project at stage 1 and stage 2. Or we can project at stage 1 and the final stage. We can project only at stage 1. We can project only at the last stage. Or we can project at S2 and the last stage. But we can show that S2 and last stage are, in practice, we combine them together. You don't have to separate the last stage and the n+1 and the final stage. Okay? So let's see what happens if we take these. So we have 4 options here. Project at S1, S2, project S1 and final stage, project at S1, project at the final stage. Okay? So the first case, we project at the first stage and the second stage. Okay, so I changed the nomenclature here because these were taken from older slides. But it's the same thing. So we first do a forward Euler, and then we do a forward Euler, then we do a projection, and then we correct. Okay? So that's the first stage. So we know that div u star is 0. The second stage, we know that div u double star is 0. And this is the final stage. That's what we just discussed earlier. And this tells us that if we check the divergence at the last stage, it's equal to div u n, which is not necessarily 0 unless your initial condition is 0. Why do I go back to the initial condition? Because if you start with the wrong initial condition, with the initial condition that's not divergence-free, that's just going to carry along. It's just going to be a source term. You'll always have some divergence. Okay? Okay, what about option 2? We project at the first stage and the last stage. So one fix to this is to say, hey, let's skip the second projection and project at the end to make sure un+1 is divergence-free. Makes sense? Because that's the problem we had. We had a problem. If we projected at S1 and S2, final stage was not divergence-free. You can project the final stage, but now you're doing 3 projections, and that doesn't make sense. Because the second stage, in reality, this second stage, you don't compute it explicitly. You can just take it and put it in here. So you only need one stage and the final stage, really. In practical terms, you don't compute this explicitly. You compute phi star, and then you bring phi star and expand it over here. Okay? So the second stage really doesn't exist. You only have a final stage. Okay, so this is the right way of doing it, is doing a projection at stage 1. So div u star is 0. At stage 2, you don't project. Just do a guess. But then at the final stage, where we are averaging, you have 1 over 2 un plus 1 over 2 u double star. That's not divergence-free. And from this guy, you subtract a pressure. You correct this guy in the last stage. Okay? You correct it in the last stage. So now that gives you an equation for the pressure, and you can show that div un+1 is 0 right now. So this guarantees that your new velocity field conserves mass. But is it second order in time? Yes, it is second order in time. Because what I did here is just a trick. I don't need to explicitly separate stage 2. I can combine stage 2 with the final stage. So there's no stage 2. So we only need to project at stage 1 and the final stage, okay, for RK2. Okay, what if you project only at the first stage? So u star, you do not project at u double star. You don't project at the final stage. Of course, you're not going to be divergence-free. Because div un+1 is going to be div un and div u double star. Div u double star is not divergence-free. Okay. Now, the problem here is that we have so many projections. And if you go to RK3, same thing applies, RK4, RK10. If you're crazy enough, you want to do a 10th order in time. The problem is you're doing a projection at every stage. And one of the questions is, if we are concerned about mass conservation for the final stage, why are we doing projections in the intermediate stages? Don't project. What if we don't project in the intermediate stages? So what if we just get the first slope, the second slope, and then only project at the last stage? Okay? So that changes your equations a little bit. We guarantee that div u n plus 1 is 0, but the question is this still second order? And this is actually Mokbil's dissertation, is to look at what happens when we do not project in intermediate stages. Do you want to summarize some of your preliminary results? If you don't do the guesses he's talking about, you will lose accuracy. So you don't project, you don't do a guess, you only project at the end, you're not going to get second or third order. Okay? You haven't done anything. You're just essentially doing a very costly forward Euler. Okay? A costly forward Euler. The other option is to project at every stage, which is very costly. But if you use Mokbil's estimators, you can guarantee second order and not do projection, or third order and not do projection. Anyway, pretty neat stuff. We'll invite you to his dissertation defense in a couple of years. Okay, so this procedure can obviously be generalized to any RK scheme, but you may end up with a large number of costly projections. So why are projections costly? You know, yeah. It's because of the linear solver. So think of this, think of that you're doing this on a supercomputer. And the Poisson equation, the pressure matrix, combines all of the processors on the supercomputer. So if you remember James's slides and presentation on parallel computing, you have a global matrix that spans, some people don't comprehend this, but you have a matrix that may have 5 trillion degrees of freedom in it. It's huge, and it grows across processors. And that is very costly to solve because you need to solve the whole thing together, not locally. So you're communicating all the time. That communication is very costly. So projections are costly. Linear solves and nonlinear solves are costly globally. Okay? All right. Boundary conditions, I'm just going to go over that very briefly just for completeness. We know how to do walls and moving walls as long as the wall is tangential to the motion. Okay? We know how to do inlets. They're essentially kind of similar to how we did walls. And outflows was the elephant in the room. And in your project 2, I suggested you implement one outflow condition, which was based on making sure that the flux or the derivative of the pseudo velocity or the uncorrect velocity, that's 0, and you set a value for the pressure. Today I'm going to show you how you do it for du by dx equals 0 on the primitive variable directly. And it's not that complicated, but the implementation can be a little bit confusing. Just like with the implementation of the one you did at homework 2, you had to maintain your for loop and do the pressure gradients at the boundary, you had to set the pressure in the Gauss cell intelligently. So again, what we do, we apply continuity at the outflow. And first, recognize that in this case, so you're doing a plus wall on the plus side. So du by dx equals 0. We're just going to do a first order approximation. And so u east minus u west over delta x, that's equal to 0. So in other words, u east n plus 1 is equal to u west. So you think of U east as the cell right at the outflow boundary. So if your flow is coming this way, this is U east and this is U west. U west is the interior cell, and U east is the cell is the face right at the boundary. Okay. Now, just like we did with with other outflow, we take the continuity equation, and we use that. Remember, the pressure equation, where did it come from? It came from the continuity equation, okay? So what does the outflow do to that pressure equation? So we got to take the continuity equation and apply it at an outflow cell, okay? At an outflow cell, and see how it modifies the Poisson equation in those cells right next to the boundary, okay? So for the continuity equation, this is what we have, okay? U east minus U west over delta x plus V north minus V south over delta y. Now U east minus U west is equal to 0 because that's implied by this condition. So that leaves the continuity equation with this term, V north minus V south over delta y equal to 0. Now we apply our projection splitting on these guys to get the Poisson equation for the pressure at the outflow. And you can immediately tell what we did. We dropped the coefficient 2. We dropped 2 from the coefficient of the cell center because these guys are canceled out, and we dropped the east and west coefficients for the pressure. So you can get that pretty quickly. So in other words, that's what happens to the Poisson equation at the boundary. So you reduce your main diagonal coefficient by 2, and you get rid of the east and west coefficients, okay? Now, I didn't give you this condition in your homework, in your project too, because if you're not using an iterative solver, this is going to result in an ill-conditioned matrix. So you have to use an iterative solver, okay? So that's the problem with this outflow condition, okay? So you can't use an SP solve, for example, or sparse solve. You got to use an iterative solver with this. But that's it. That's all you have to do. Modify your Poisson equation there, but make sure you set your velocity at the boundary using the interior velocity. If you don't want to do that and you want to do it as a pressure gradient, you have to derive a value for the pressure in the ghost cell. And you do that from this condition, okay? You do that from this condition. You say U east as n plus 1 is U star minus delta t grad p, and then you derive grad t you derive p or grad p from these values, okay? All right. Next item on the list, all awaited for collocated grids, okay? So the staggered grid is a nightmare, annoying as hell. Computing kinetic energies on staggered grids is very annoying, but staggered grids are unique because they actually, you can show that they preserve kinetic energy, the kinetic energy of a scheme, okay? But they're inconvenient for many problems, especially problems with smooth, complex geometries that have kind of smooth moving surfaces or non-rectangular surfaces, okay, where you can't really put in a staggered grid, or non-uniform or unstructured grids. They're really hard. They're really annoying to do. So we'd rather do our formulation using a collocated grid. And while the staggered grid is extremely robust, it's difficult. It's not very useful for practical applications or many practical applications. But it's still in use, surprisingly. I mean, we use it in our code, even with complex geometry. We just stair-step the geometry like you did in your project. And if you want better resolution, we refine and refine until we get a nice, smooth representation at the boundary, okay? But with collocated grids, we don't have to worry about this. And so what's the difference between the staggered grid and the collocated grid? Yeah. So in the staggered grid, we solved for scalars at the cell center, and we solved for the u velocity on the x faces and the v velocity on the y faces. With the collocated grid, we put everything on the cell center, okay? But we are still finite volume, so we need a u east and u west and p east and p west, right? Because we're finite volume. We're integrating over the volume, which is going to give us a surface integral, so you're going to need values at the boundary. But don't confuse u east with the with Uij. This is where we're solving the result of doing the integration of the governing equation is going to live at the cell center. Okay, that's where we're storing our variables. Okay. So I'm going to revise. I'm going to review, not revise. I'm going to review the the checkerboarding problem. Okay, I'm going to derive it in a different way today. So again, our scheme consists of doing a time advance for the Navier-Stokes without the pressure, and this is self-centered here. Okay, everything is self-centered, so your operators are all based on the integral cell-centered. Whatever it takes, you just figure that out. But it's not going to be an issue for the momentum equations. Okay, and then we correct with the pressure, saying un plus 1 is u star minus delta t grad p. Okay, now I'm going to apply this to u star and to v star separately. Okay, and notice now for un plus 1 we have a p east and p west, and for vn plus 1 we have p north and p south. Right? We're doing the pressure gradient. Okay, and the north and east, they live at the centers of the edges. Okay, so one simple way of doing this is taking a simple average. For p east is the average of the east value and the ij value, so that's pi plus 1, so essentially pi plus 1 plus pi over 2, so that gives us p east, and same thing for p west, it's pi plus pi minus 1. Same thing for p north, pj plus 1 plus pj, and p south, pj minus 1 plus pj. Now notice I don't put the I index because it's I. Okay, that's great. Now the momentum equations are not a problem. They don't cause a problem, but it's the continuity equation that's a problem. So what happens with the continuity equation? If you assume dx and dy are equal for simplicity of the presentation, this is what the continuity equation gives you. U east minus U west, right, over delta x, plus V north minus V south over delta y. If delta x is equal to delta y, you get rid of that, so you get this combination. Okay. So now, how do you compute U east, U west, V north, and V south? You could say, okay, I'm going to take a simple average. Remember, in the staggered grid, our unknowns lived here. So we knew the values of U east and U west from doing the time advance. We knew those values because they lived there. In this case, they don't. The unknowns, the dependent variables, they live at the cell centers. So we have to do an average to compute the value at the face. We have to do something to compute the value at the face. And what we do, we just take a simple average like we did with the pressure. Okay? And now, so what is I plus 1 and I and I and I minus 1? We take these equations and put them here. Okay? So Ui plus 1 is U star I plus 1 minus delta T, the pressure, P east east and P west west, etc. It gets a little bit nasty, but once you do all the surgery and the operations, this is the resulting equation for the pressure. So we took the continuity equation, substituted the velocity, took the average, and got the pressures all involved. And remember, the pressure equation, the pressure plus 1 equation was some form of a set of pressure coefficients, or del squared P equal div U star in the staggered case. So in this case, what we get is the classic decoupling problem. Points at ij are connected to I plus 2 and j plus 2 and I minus 2 and j minus 2. So we're skipping every other point. We showed this early on. We were showing it in a different way now. So that's checkerboarding. And same thing for the divergence. You're not connecting points at ij. You're connecting points I plus 1 and I minus 1 and j plus 1 and j minus 1. It's a very wide stencil. And that causes the classic checkerboarding problem. Okay. Okay, great. So we know that's an issue with the collocated grid. Our goal is to tighten that stencil. Okay. So Ree and Chow in 1983 came up with a remedy. It's called the Ree-Chow interpolation, if you've heard of that. It's very common for collocated grids. In the unstructured world, they call it also the pressure stabilization term. And I'll discuss at the end what it effectively does. Okay. So instead of making the cell-centered velocities divergence-free, what Rie and Chow did is said, okay, let's make the edge velocities divergence-free. Okay, so rather than saying u east is the average of ui and ui plus 1, I'm going to make u east divergence-free, so make u east equal u star east minus delta t grad p, and u star east is going to be the average of u stars. So effectively what they said, we're going to pretend that we're using a staggered grid. Okay, it's a little trick, right? But it has issues. Okay, so we go back to the continuity equation again. Instead of interpolating u east and saying this is equal ui plus 1 plus ui over 2, and then saying ui plus 1 is u star I plus 1 minus delta t grad p, what they did, they said, okay, interpolate the intermediate velocity. So we have u stars living everywhere. Let's make u east star equal to the average, and then correct u east n plus 1 using this form. Okay? The way to think about it is rather than making the centered velocities divergence-free, we make the edge velocities divergence-free. When you do this, you go and substitute in the continuity equation. We said that u east star is 1 over 2 ui plus 1 plus ui star, and then u east n plus 1. This is where we're correcting. We're doing the projection on the faces, essentially. You go and substitute, and you recover your nice compact stencil for the pressure. So we've effectively pretended that we're using a staggered grid. Okay? And proceed as usual with the momentum update. The pressure, you do it the same way we did it. Okay? And that's what you get. Now, the problem with this, and if you remember when we did the finite difference formulation, I said that although we were solving the Poisson equation with a tight stencil, when we take the divergence of the actual equations, we ended up with a wide stencil. That's effectively the same of what we're doing here. Except in this case, your divergence, your edge velocities are divergence-free. So your div u is 0 at the edges, not at the cell centers. So you're committing an error. You're still committing an error. Okay? But there's an analysis that shows that the Rie-Chow approximation, what it effectively does, it adds a fourth order term, which is a diffusion term, to the evolution of the pressure in time. And what does fourth order diffusion do? It kills oscillations very fast. So any oscillations you get from the checkerboarding are going to die out immediately. Okay? That's what it does. It's a little bit complex, the analysis, but that's what you learn when you take read a theorem, you take it and use it as a tool. Okay? Collocated grids. That's how it's done. And the final topic in these slides is this. Compressible, low Mach, incompressible. What's the difference? So one thing you may be confused about, and I saw that in some of the projects being proposed, you got to be really wary about algorithms for compressible flows and incompressible flows. And why do you think that's the case? So our methods will work, standard numerical methods, you take them and apply them to the gas dynamics equations, they'll work out of the box. Really what this class was dedicated to for the most part is learning about the projection method, how you untangle the pressure and velocities. But for the full gas dynamics equations, you don't have that problem. You have 3 momentum equations, 1 equation of state, and 1 energy equation. And you have 3 unknowns. Well, you have U, V, W, P, and T or rho. And so you have enough equations as there are unknowns. Okay? Actually, you have no. Yeah, so you have 3 momentum, 1 continuity, so 4 equations, and then 1 energy, 1 equation of state, and you have rho, U, V, W, P, and T as unknowns. So you have 6 equations, 6 unknowns. You can solve the problem. You can do an explicit method. It takes you forever to propagate a pulse, but you can do it. You can do the flux limiter, so that's not a problem. But now the question is, can you use that method, can you use those equations for incompressible flows? And what's the difference? Why do we distinguish between incompressible flows and compressible flows? Because the equations of gas dynamics, they should behave, in the limit, they should recover solutions, incompressible solutions. You have pretty much no density variations, or in other words, the Mach number is nearly 0. So what's the problem? Why don't we do that? Because it's really expensive. Why? No. 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 Come on. No. Okay. Do you wanna think about it a little bit before I give you the answer? Why is it so expensive to use the full gas dynamics equations and drive them to very low Mach number or to the incompressible limit, where there's minimal density variation to none at all? Okay. I'm going to show you some math first, okay? And then it all has to do with time scales. So, okay, I'm going to do this. What happened here? What? Uh-huh. Uh-huh. Okay, so therefore, there's 2 time scales. There's the scale. You instantly heard the sound. That's a shock wave. That's a steep wave, okay? You instantly heard the sound, but also by clapping my hands, I moved some air away, but you barely felt it. You're probably going to feel it after an hour because of the advective motion. So there's 2 time scales. The very fast acoustic time scale that carries sound, and the very slow advective scale that carries the fluid. And if you take the full compressible equations, you are stuck by the acoustic time scale. The incompressible equations, they don't have that. They eliminate that by virtue of the div u equals 0. So if we get a chance to do that lecture next week, we'll show you this mathematically exactly, how the incompressible equations eliminate the acoustic waves. Okay? So let me discuss this a little bit more mathematically. I'm going to look at the Euler equations, and we actually know how to do this, how to show that we have u, the advective time scale, and the acoustic time scale embedded in the equations. Okay? So those are the Euler equations. I presented them early in class. You have, it's written in this form. You have as in a flux form. Okay? So Euler is infinite plus compressible, and we define the u vector as rho, rho u, rho v, rho w, and rho internal energy, and then the E flux, F flux, and G flux in all 3 directions. But for simplicity, I'm going to take the 1D case, where you only have the continuity. So d rho by dt plus d rho u by dx equals 0. The momentum equation conservation form, d rho u by dt plus d rho u squared by dx plus dp by dx, and d rho e by dt plus d rho e plus p over rho u dx. Okay? And you have all of these kind of state relations for an ideal gas. And no specific assumptions have been assumed here, calorically perfect. You can simplify these quite a bit. But the bottom line, I'm not interested in the solution of these equations right now. I'm interested in their properties. Okay, so I'm going to turn this into characteristic form. And if you remember our lecture on characteristics, if we write these equations in this form, du by dt plus a du by dx, then the characteristics are found by looking at the eigenvalues of the A matrix. Okay? And you can prove to yourself that if you transform the conserved form of the equations to non-conservation form, where you have rho u and e rather than rho and rho u and rho e, this is the coefficient matrix here. Okay? You rho, u 1 over rho, and rho c squared plus u. What is c? That's the Mach number. Okay? That's the speed of sound, sorry. Okay, so the characteristics are found from the eigenvalues of this matrix. To get the eigenvalues, we have to solve this polynomial determinant of A transpose minus lambda I equals 0. So the roots of this polynomial are the eigenvalues of the system. Now, what are the eigenvalues? They represent the characteristics. What are the characteristics? Remember, in the characteristic discussion, can we find lines on which the ODE becomes a PDE? And on those lines, the ODE is going to move at those speeds along the line. So you can think of the initial condition moving as fast as where those lines are. Okay. So it turns out that the determinant of this whole thing, a minus lambda I, you get this form, u minus lambda times u minus lambda squared minus c squared. And the roots, you have three roots. Lambda equal u plus c, and lambda equal u minus c. So what does this tell us? So this characteristic moves information at u. What is u? That's the advective motion. That's the motion of the gas, the motion that you see. Okay? But there are two other characteristics, one moving to the left and one moving to the right, u plus c and u minus c. And what are those? That's an addition, that's the speed of sound. So on top of the speed of sound, we're moving information at the advective motion plus the speed of sound. And if your advective motion is 1 meters per second, and your speed of sound is 300 meters per second, you're moving information both at 1 meter per second and at 300 meters per second. Okay? And that's the problem. That's the problem. You have two significantly disparate, separate scales. If your advective motion, u, approaches the speed of sound, that's not a problem. Then your characteristics are c, 2c, and 0. You can go explicit. So that's Mach number equal 1. For very low Mach number, u over c is very small. Okay? So you could, yes? No, you have information traveling in all directions. Yeah. This is don't worry about the sign, because you have u minus c and u plus c. The sign is not a problem. The direction is not a problem. It's the speed at which they're moving. So that's the right way of thinking about it. So then, but as you increase the Mach number, you're approaching, then your u could be 10c. So then you have another problem. Your advective motion is faster than your acoustics. Okay, so it's a problem of time scales. That's why you can take the fully compressible equations and drive it to low Mach. But it's going to be so expensive to solve. Because what is the constraint on your time step going to be based on? No, it's going to be based on c, because that's the fastest scale. Remember, you cannot move information by more. The fastest information cannot move by more than one grid point at a time. So let me show you this. Okay? And so we learned now that gas dynamics, the gas dynamics equations, they describe two types of motion: the bulk fluid motion that you see, and acoustic waves. Okay? So let me show you the clap example. Okay, this is Schlieren. So you see the pressure waves. They're like, you can barely even capture them. This is a high-speed camera. You see the advective motion over here from both clapping the hand and some of the heat, some of the buoyancy coming up from the warm hands. But look at this. Look at how fast. By the time this fluid particle moves by less than a fingernail, half of a fingernail, the acoustic wave is gone. It's moved about a meter out. 2 time scales. So if you want to capture the acoustic waves, you have to step at the time scale of the acoustics of the speed of sound, which is going to limit your time step. Okay. So numerically, on a computational grid, we're going to look at a fluid front or a gas front. So that's the vortex that is forming and that is spinning. And that's moving at a velocity u. That's the advective motion. And then you have acoustic waves moving at u plus c and u minus c, which are moving in all directions. These are the sound waves. Okay. So now let's ask the question, what is the distance traveled by information in each time step? So we have 2 types of information: information moving with the acoustics and information moving at the advective scale. So in a single time step, the acoustics move at u plus c delta t, or u minus c. Let's just, for simplicity, take u plus c delta t. Okay. And for the gas is going to move by u times delta t. So this is a distance, right? Meters per second times second, that's meters. Okay. So this is a distance, small delta x. Now stability is going to require that you do not move by more. The fastest information in your grid does not move by more than one grid point at a time. So in other words, your stability is going to require that delta t is less than delta x over u plus c. Okay? Because u plus c is the fastest information, absolute value, fastest information on your grid. That's your time stability constraint. Now you can take this guy and manipulate it in a way to make it a function of the Mach number, just like we did with the previous time step, made it a function of the Reynolds number. We're going to make this a function of the Mach number, but also count the number of time steps. If we were to use this algorithm, this method, I want to count the number of time steps that it would take a fluid front, a vortex or a flame, to move by one grid point as a function of the Mach number. Make sense? So I want to count how many time steps do I have to take in my algorithm to move my fluid front that moves at u by one grid point using this stability constraint. And this is what you get. On the x-axis, I have the Mach number going from 10 to the minus 4 all the way to 10. Okay? And on the y-axis, I have the number of time steps. Okay? How many steps do I have to take as a function of the Mach number? Okay? So at Mach number 1, the number of time steps is 2. So all I need is 2 time steps to move the fluid front by one grid point. And the larger the Mach number, the more I approach 1. So one time step, I move everything by one time step. So that's not a problem here. We can go nicely explicit. But what happens at low Mach numbers? What the heck? At 10 to the minus 3, you need 1,000 time steps. 1,000 time steps for a low Mach number. So that's a Mach number in the atmosphere, okay? Where your advective motion is what? Maybe not the atmosphere. Maybe here in the room. So you have 10 meters per second. Your Mach number is order 10 to the minus 2, 10 to the minus 3. That's a problem. If you want to resolve your fluid motion, you're going to need 10,000 time steps. Now, why is this a problem? So if we do this, we will resolve the acoustic times acoustics. Okay? So I'm talking to you, or you have a fan blowing air. Do I care about the sound coming from the fan? Not necessarily. I may care if I'm looking at noise propagation, but there are models for those. But I may care, and then I can justify using this algorithm. But if I'm interested in the flow of the air conditioner here that's blowing air into the room, I don't give a crap about the sound coming from this vent. What I want to look at the fluid flow. But this is forcing us to compute the acoustics, okay? And so I have to add on top of this that in this entire regime, up to Mach number 0.3 in practice, the acoustics, not only do they not matter necessarily, they may be just insignificant to the structure of the flow. So go and sing to a candle. Does anything happen to the flame? You're probably going to extinguish it because you're blowing air at it, not because of your singing. Okay, so the sound is not going to affect, it does not have a leading order effect, at least for kind of these simplistic flows in this regime. Okay, so it's a problem. This regime, this entire regime is a problem. We should not use the full gas dynamics equations to resolve. We still have 2 minutes to resolve these low Mach regimes. So this is colloquially known as the low Mach regime, okay? An incompressible flow is kind of just over here, okay? So for low Mach, the advective motion is much smaller than the speed of sound, yet our stability is still dictated by delta x over u plus c. But what we want is for stability to be dictated by the advective motion. And that's what effectively happens with the set of equations for incompressible flows. So you can derive the incompressible flow equations by making these assumptions in the full gas dynamics equations. So you take the full gas dynamics equations, you perturb them, you do some fancy math, and you get rid of all the acoustic terms, and that leaves you with the incompressible equations, which will allow you to time step at the advective motion. But you have to pay the cost of a linear solver. So effectively, what the linear solver does for the pressure, it almost instantaneously adjusts the pressure waves that you would have had to compute from the compressible algorithm. So within a single time step, it makes the pressure waves somehow implicit, and you resolve the pressure waves instantaneously much faster. Okay? So let me show you a simulation that I did for a problem that is pretty similar using a low-Mach algorithm. Think of incompressible flow algorithm and a fully compressible algorithm. I tried to make the problem as identical as possible. You cannot get it exactly the same because you have diffusion coefficients and heat transfer coefficients and a bunch of other properties for the full gas make it equivalent to the formulation of the low Mach. But they are qualitatively almost identical. So on the left, you're going to see the compressible algorithm. On the right, you're going to see the low Mach algorithm. This is a heated blob in a room with a gravitational field. So there's gravity pulling down, okay? And this is a hot blob. So colder air is going to go down, pushing, due to mass conservation, is going to push this blob up, okay? So it's going to go up. Now, the compressible simulation took 5.8 hours. The low Mach simulation took 58 seconds. And I tried to round the number a little bit. So it took 360 times more time to do the compressible simulation than it was to do the low Mach simulation. Let's see. Structurally, they're not that different. Now, the reason this behaves slightly differently here is because we are using limiters over here. Okay? We're doing upwinding over here, but the behavior is nearly identical. Okay? So which algorithm would you use with this case? I want to use this guy. Okay? This guy is forcing me to resolve all the pressure waves. If I plot the pressure, you can see pressure waves going back and forth until they reach equilibrium, and that's very expensive. Okay? So now the way to resolve this is either choose an appropriate algorithm for the flow you're dealing with. If you're low Mach, use a low Mach algorithm or incompressible algorithm, or use a high-speed compressible algorithm. But there are also methods that work at all speeds, and that gets us into an entirely different world. There's preconditioning, and there is methods for all speeds, so where the preconditioning works. There's an extension of the simple type algorithms going all the way to fully compressible.